Alright, so where I ended the last video was with problem 7. In this one, in problem 7, just to remind everybody, we're going to use the mass of the sun, and then everything else is just a constant. I'm going to do one quick example. So here's my example. Let's say we had something that was the mass of the Earth. One thing I should point out is the Schwarzschild radius. This thing called the Schwarzschild radius. You can calculate the Schwarzschild radius for anything that has mass. Now, keep in mind, it doesn't mean anything in the universe is going to turn into a black hole. The conditions for which something can be a black hole is when there's a dead star that is where the remaining mass is greater than 3 times the mass of the sun. So this mass right here in the Schwarzschild equation, there's a condition on that for it to be a realistic black hole, that has to be greater than 3 times the mass of the sun. So nature doesn't produce black holes except in extreme situations. All right, so because we can do this theoretically, let's calculate the Schwarzschild radius for the Earth. All right, so here's the mass of the Earth, 6 times 10 to the 24th kilograms. And then, so to calculate the Schwarzschild radius, it is 2 times big G, 6.67 times 10 to the minus 11th, times the mass of the Earth, 6 times 10 to the 24th, divided by the speed of light, 3 times 10 to the 8th. But you got to square that. That goes in the denominator. Then when you do that, just to give you one nice example, this turns out to be 0.008 what is it? 889. So I'm just going to round it to 0.0089. All right. So and the answer is in meters. All right. So that always with the Schwarzschild radius, the answer is always in meters. All right. I'm going to do number 9. All right. So for number 9, this is the last one. I wish I could have gotten this on the other video and just had one continuous one. But anyhow, given the so this is material that is in the what's called the accretion disk, that is basically around a black hole. It's rubbing against itself. Friction is causing it to heat up to 10 million Kelvin, and so that's given to us. Given the temperature of the accretion disk is at 10 million Kelvin, find lambda max. And then what they ask us to do is, once you find lambda max, you have to figure out what part of the spectrum, the electromagnetic spectrum, that is in. All right, so anyhow, we have, of course, this equation. It's called Wien's law. The temperature in Kelvin is equal to 2.9 times 10 to the 6th divided by lambda max. Algebraically rearrange that equation, since we know what the temperature is in Kelvin, right? We know this value right here, and so we plug in 10 times 10 to the 6th into this equation, and that'll give you some number, right? And that number, the number that they give you, is going to be in nanometers. All right. So that's important. So just take 2.9 times 10 to the 6th divided by 10 times 10 to the 6th, right? Which essentially is 2.9 divided by 10. Anyhow, try that, and that will give you the number of nanometers. If you use the table on page 93 of our textbook, you'll find what part of the electromagnetic spectrum this is in. That's the second little part of this problem number 9. All right, so make sure you do this homework. This is homework number, what homework was this? This was number, let me verify, number 16, homework 16. All right.